Hello everyone, welcome back to our educational video. So the topic which we have started here before, that is crystal field theory. In last video we have been seeing the basic and historical perspective of crystal field theory and as well as the splitting of energy level. So in this video we are going to discuss about John Taylor distortion. So the octahedral complexes, that is we also call it as ML6, in which all the 6 ligand are equidistant from the central metal ion, that is with the equal metal ligand bond length, and they are regular or symmetrical octahedral complexes. In some octahedral complexes, all the 6 bond length are not the same as their shape get changed or distorted. Such octahedral complexes are also called as distorted octahedral complexes. So it has been observed that some octahedral complexes with the metal having certain electronic configuration distortion from symmetrical geometry which has taken place spontaneously. So in 1937, John and Taylor, both of these scientists, had put forward a theorem to explain why certain complexes undergo distortion from perfectly symmetrical geometry. So this theorem states that for a nonlinear molecular system, which is electronically degenerate state, distortion must occur to remove the degeneracy and lower energy level of the system. So as the energy of the system is lowered, it gets stabilized. So this statement is called as John Taylor effect, and the distortion in the geometry of the nonlinear molecule is called as John Taylor distortion. We will see here the example how the distortion taken place, and the John Taylor effect is one of the factor that help us to understand the stabilization of some complexes. Now, John Taylor effect is usually experienced by octahedral complexes with unsymmetrical distribution. So let us see here the example, that is the copper 2 binary. We find the 3 electrons in orbit under the group Eg will arise by either of the following, that is dz square 1 or dx square minus y square bracket square or dz square square and dx square minus y square. So in the first case, would we expect the power of expulsion is higher among the electrons of a metal ion, and the group giving the direction of the axis, that is dz square, than in the direction of dx square minus y square. And this we will be the link in the direction, that is dz square, longer than the link of the 4 direction, that is dx square minus y square. So this is giving you elongated structure. In the other case would be exactly the opposite sense of a direction made by 2 shorter, that is dz square, and 4 link longest direction, that is dx square minus y square. So this is the another case of complex. The first case was elongated and the second is complexes. In practice, the latter type is rarely a result. Group Eg and T2G is no longer having same energy, that is degenerate, but separated as in the following figure. Look into the figure how the levels are separated. There are 4 electrons in dxz and dyz orbital, then 2 electrons, paired electrons in dxy, then the one pair of electron is in dz square, and only one electron remains in higher or excited state, that is dx square minus y square. So this is the d level in the weak field, that is tetragonal of copper 2 complex. Now, distortion for the octahedral or tetrahedral is what is known as the impact of a John Taylor, which is stated as it found under the orbit, that is subshell Eg or T2G, which is unsaturated or half saturated or empty. The distortion of the previous types occur and result in separation at level that have the same energy. In the previous case was the difference in number of electron is a set Eg, and the difference if the number of electron in the orbital T2G in the octahedral. So this happens distortion simple because the orbits, that is dyz, dxz and dxy components of the group T2G indicate between the axes which do not refer to the group coordination directly So the asymmetric in the electronic density of these orbits will not affect much in the spatial structure of a complex. The following table shows the electronic configuration cause distortion. John Teller. Look here, if the distribution of electron in the group of orbit is D2G1 and EG0, then the electronic structure is D1, and this is the weak type of distortion. Then T2G2 EG0, that is D2 electronic structure, T2G4 EG0 D4 electronic structure. These all structures are weak, shows a weak distortion. Then fourth one is T2G3 and EG1, which is high spin D4 electronic structure, and this is having strong distortion. Then T2G5 EG0 D5 low spin, so this is also a weak type of distortion. Then T2G4 EG2, T2G5 EG2, these are D5, D6 and D7 electronic structure, which are weak distortion, but D5 is low spin type of, and D6 and D7 are high spin type of. And at last T26 EG1, T2G6 EG3, that is D7 and D9 electronic structures are having strong distortion. So another type of distortion but does not result from influence of a John Teller in case of nickel 2 complexes hexagonal coordination. If you find 2 group coordination a weak field and 4 group giving a strong field, in this case the happens distortion does not produce the effect of a John Teller but results in unequal field resulting from the group coordination, leading to it separation of both dx square minus y square enough as is shown in the figure. Look here, the d orbitals of nickel complexes are separated into 4 levels, that is the highest level is dx square minus y square, then dz square, then third is dxy, fourth is dxz, and last and the lowest orbital is dyz. So separation of orbits d in the complex nickel to d8 under the influence of 2 groups coordination, a weak field, and 4 group coordination, a strong field. So at last, I would like to tell that John Teller effect is usually experienced by octahedral complexes with unsymmetrical distribution of d electron, particularly in Eg orbital with directly face to the ligand. The asymmetric filling of Eg orbital makes some ligand to face more repulsion than other ligand, resulting in distortion of octahedral geometry. So John Taylor distortion therefore more common among octahedral complexes with asymmetric distribution of electron in Eg orbital of metals. Then John Taylor distortion also observed in complexes with unsymmetrically filled T2G level, but in general extent of distortion is less compared to the distortion shown by unsymmetrically filled by EG level. So John Taylor effect is observed in octahedral complexes not only with negatively charged ligand but also neutral ligand that are polar. So here we have successfully completed John Teller effect. This topic is about coordination chemistry and having metal ligand bond formation. So this is how we have completed John Teller distortion of crystal field theory. So I hope you must understand the crystal field effects and on the octahedral complexes which is shown by John and Teller in 1937. So in next video we will meet with new topic of crystal field theory. Till then, thank you and bye bye.